Hi guys, welcome back. Today we're going to be talking about those 5 types of equations that we listed in our previous video. So we're looking at combination, decomposition, single replacement, double replacement, and finally combustion. And we're going to look into all 5 types of reactions today, how to predict their products and how to recognize them. Our first type of problem is called a combination reaction, and this is where 2 or more substances combine, surprise, to form a new compound. So this one is kind of like chemical marriage. This is like a 2 become 1 kind of deal. In this kind of a setting, what we're going to see is A plus X yielding AX. And so it's an important distinction to know that when we're talking about something like A, this is referring to a metal, and metals are sometimes abbreviated by just M. And then X, the end of the alphabet, these represent nonmetals or NM. And if you recall from our previous study of the periodic table, there is a stair-stepping line that comes down through the P block. And this stair-stepping line separates the metals, which are down left of that stair-stepping line, from the non-metals, which are upright. So we've got our metals from our non-metals. When we use the abbreviation A, we're talking about something that's a metal, and X is a non-metal. So when we put this together, we're identifying an ionic compound. So if we look at some examples of this, we could see H2 plus O2 yielding H2O. So in this case, we have H2, which is our metal, and O2, which is our non-metal, and they are combining to form H2O. Once we have H2 plus O2 yields H2O, we do need to balance it. We need to keep in mind how many hydrogens and how many oxygens we are seeing. So even though we haven't totally learned how to balance yet, I do want to go over what balancing equation like this might look like. We want even numbers on both sides of our reaction symbol. So we usually draw a line down the middle to tell us that we want equal numbers on each side. So you can start out by keeping track. How many hydrogens do I have on the left? I have 2. And how many oxygens do I have on the left? I have 2. And now we check the right. How many hydrogens? 2. How many oxygens? 1. So when we think of balancing, what we want to see is the same numbers on both sides. So I know that I need to have 2 oxygens. So this is where those coefficients come into play. We're going to put a coefficient up top. 2 times 2 gives me 2 oxygens, but it also inadvertently gives me 4 hydrogens because 2 times 2 is 4. So in balancing my oxygens, I messed up my hydrogens. So now I have to go back to the other side, and I'm going to put a 2 here to fix that because 2 times 2 equals 4, and I'm all balanced up. Now we're not going to put a lot of emphasis on this just yet. This is really the second half of the chapter, but I wanted to kind of introduce the concept that even once we have predicted the products and we know what we're going to make, we're not done until we've balanced the. This next problem allows us a chance to try to predict the products on our own. So we start out with Mg plus Cl2, and we want to know what are we going to make from this. So when it comes to predicting, the first thing you need to do is identify the charges of the ions. So I would go to my periodic table and find magnesium. Magnesium is in group 2, so I know that magnesium has a charge of Mg2+. And then I would go again to my periodic table and look for chlorine. Chlorine is in group 17, so chlorine has a charge of Cl-. Now, to figure out what they would make when I put them together, I would crisscross and reduce, just like we did in chapter 9. So Mg2+ and Cl- crisscross and reduce to form MgCl2. That is the predicted product of this synthesis reaction. And incidentally, it's also balanced. I have 1 magnesium on the left, 1 magnesium on the right, 2 chlorines on the left, 2 chlorines on the right, and I'm all set and good to go. Our next kind of problem is called a decomposition reaction. And decomposition breaks apart what combination put together. So in decomposition, we're going to take that single compound and we're going to bust it into two simpler pieces. This usually requires some energy, some smashing to get in and break it apart, but it is generalized by the formula AX, right? One thing breaks apart into A plus X. So one example here is looking at water breaking apart. So if we break water apart with electricity, we can split our H2O into H2 and O2. Once again, it's very important here and very commonly missed that if something is in that little grouping, we say they're the 6 in the shape of a 7. I'll remind you of that when we switch to the other camera. The 6 in the shape of a 7 or hydrogen, they come with this little 2 whenever they are by themselves. They don't like to be otherwise by themselves. 2HGO, mercury oxide, can also break apart with heat into mercury liquid and oxygen gas. And the last thing we want to do is H2O2 splitting apart. So we're going to look at that on the board. When we break apart H2 and O2, we need to consider what it's going to make. So when hydrogen comes over, it can't just be H and O. There is a group on your periodic table, the 6 in the shape of a 7, and here they are. These 6 atoms, which make the shape of a 7, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, when they exist alone, exist in pairs. They like to be alone together. So if ever you're writing one of these as the result of a reaction, like we are for oxygen, it needs to be O2. It can't just be O by itself. And it actually turns out that hydrogen is the same way, hydrogen over here. So we end up with these 6 in the shape of a 7 and hydrogen over here that always have to come as a pair. So the results of this decomposition reaction break into H2 and O2. And this also happens to be balanced, 2 hydrogens, 2 hydrogens, 2 oxygens, 2 oxygens. So we happen to be good to go and done with our decomposition reactions. Our next kind of reaction is called a single replacement. And as I mentioned before, a single replacement reaction is like a direct substitution. If you've ever played a sport, and this is where it'd be nice to be talking to you guys because I like to use the sports you play, but if you have ever played volleyball, you know that a player like a middle blocker can only be subbed in for a player like a middle blocker. The same is true in basketball. A center is going to be substituted in for a center. Or in football, a quarterback has to be substituted in for a quarterback. We can't just randomly put a wide receiver in as the quarterback. That's not going to be good for your football team. A pitcher or a first baseman needs to be substituted for a pitcher or a first baseman. If you take an outfield player and you put them as a catcher, we're not going to have any good come from that. So the same thing is true in a single replacement. If we're going to replace a metal, we're going to need to do it with another metal. And if we're going to replace a non-metal, we're going to need to do it with another non-metal. So let's look and see what a single replacement is generalized as. So for a single replacement reaction, there are actually 2 generalizations. One is A plus BX yields AX plus B. And what you're seeing here is that in this case, A is getting substituted in for B so that A is now with X and B is alone. You can do this the other way. Remember, A's are metals. You can do this another way, and a non-metal can substitute in. So B could be paired with X, and Y could cut in, so that we end up with B, Y, and X together. A great example of this is if you want to think about some high school kids who go to a dance. Maybe they're going to show up to a dance and they're going to be with a date. And while they're with the date, they're dancing with their date, and someone else cuts in the dance. And now the new couple is dancing, and the person that came with X to the dance is dancing alone. This is a substitution reaction. You can use the same analogy in sports, right? We have the substitution in, we get our pitcher needs to be replaced, so we get a relief pitcher in, and now the starting pitcher, B, is in the bullpen. They're sitting down all alone, okay, where A is now in the game. So we're just seeing this sort of substitution in. We're going to look at some examples of a substitution reaction. Our first reaction, Mg plus AgNO3. And our second reaction, K plus NaBr. And so what we need to do first is we need to write these equations down, and we need to identify the charges of the different elements involved. First things first, let's look at this one. So magnesium is in group 2, and magnesium is a metal. And silver is a metal. And nitrogen and oxygen, this is nitrate, is a nonmetal. Now we know that what we want to do is magnesium is going to substitute in for silver and kick out silver. The next thing we need to do is we need to figure out what their charges are. Mg is 2 plus. I can tell that because it's in group 2. Ag is plus, and I know that because it was memorized. And remember that silver, cadmium, zinc, and aluminum are ones I'm supposed to have memorized. So silver is plus, and NO3 is a minus charge. If you didn't know that NO3 was a minus charge and you didn't have your polyatomic ion list to look them up, you could know that because you know that it has to have an equal but opposite charge to silver in order to be in that combination. So now what we want to do is we want to make a new partnership where Mg is with NO3. So we're going to come over here and we're going to put that together. So we're going to crisscross them. Mg2 plus and NO3 minus becomes Mg parentheses NO3 2. And what's left over, sad all alone, is Ag. So what I've done there is I've taken magnesium and I've replaced silver, and silver gets kicked out all alone. And I've formed a new bond between magnesium and nitrate. Okay, let's try the next one. In my next problem, I have K and NaBr, and I want to know what they're going to form. So first I start by finding out that potassium is a metal, sodium is a metal, and bromine is a nonmetal. So I'm expecting potassium to come kick out sodium. So I'm going to have sodium alone. And what's left is K and Br. K's charge is plus and Br's charge is minus. And so when I crisscross them, I simply get K, Br. But, and here's where the drama comes in, just because you can write a chemical reaction doesn't mean that it will actually take place. Just like in your dreams, you can imagine showing up to a dance alone and splitting up the power couple of the school and taking over as whoever's girlfriend or boyfriend. Doesn't mean when you show up to the dance that's really how it's going to go. Just because you're sitting on the bench dreaming of being the quarterback, getting in the Super Bowl and driving your team down for a touchdown does not mean that that's really going to happen. In order to know whether or not it's going to go, we need to look at something called the activity series. This is in page 361 of your book, and you can see it on the next slide. This tells us how reactive an element is and whether or not it can replace. So they're listed. It's a hierarchy. Something that's higher is more likely to be in the game than something that's lower. So we look at the list, and something that's higher can replace or substitute in for something that's lower than it. but something that's low cannot replace a better player, someone that's higher on the list. So if A is higher than B on the list, the reaction will occur. If not, then no reaction. Point being, you can replace someone below you, but you can't replace someone above you. So let's go look. So this is the activity series. And so now we're going to go back to our examples and we're going to see whether or not we expect these kinds of reactions to occur. Looking in reaction one. In reaction one, we said magnesium will replace silver. To check if that's true, we need to come look at the activity series. So I find magnesium up here. Magnesium is up here. And I find silver. Silver is way down here. Here's silver. So the question is, can magnesium replace silver? And the answer is yes. Something higher on the chart can definitely replace something that is lower on the chart. So this reaction will go. This one stays. Now we can come look over here. This one says that potassium is going to replace sodium. So again, we come look at our activity series. Potassium is up here, sodium is down here. Can potassium replace sodium? Yes, it definitely can. If I had a reaction like this, ZnCl2 plus Hg, I would go look up and I would find out that zinc was a metal, chlorine's a nonmetal, mercury's a metal. So the concept here is that zinc will replace mercury. So the concept here is that mercury is going to replace and kick out zinc because the one that's single is always kicking out the one in the couple. So the question is, can mercury replace zinc? So we come look, can mercury down here replace zinc way up here? And the answer is no. So I don't have to find the charges. I don't have to crisscross the charges. I don't have to do anything else. At this point, I say no reaction and I move on with my life. So we have to look at the activity series to make sure the reactions actually take place. In our next kind of a reaction, double replacement, what we see is a straight swap of partners. So we have this AX plus BY, and it yields AY, right? A is now with B's partner, AY plus BX. So this is a more complicated kind of swap. In a scenario like this, we are swapping a metal for a metal, and we're making two new partnerships. In order for this to happen, one of the partnerships needs to really be worth it, chemically speaking. And so the way we know that something is really worth it, chemically speaking, is that we see the production of a precipitate or a gas, or we see water. So the things we're going to be looking at in this setup is for one of these products, AY over here or BX over here, to have either a little S in parentheses for solid or a little G in parentheses for gas, or that arrow down to show that a precipitate formed, or that arrow up to show that a gas formed. We're going to want to see one of those symbols in order to feel like we know what the product would be. We're going to predict very few double replacement reactions because they involve the solubility table, and the solubility table is tough enough to teach in person, but I'm definitely not attempting it across the internet. So we're not going to predict the products of double replacement reactions this year, but you will need to be able to recognize that a reaction is a double replacement reaction. And last but not least, we see the combustion reaction. Combustion reactions are very formulaic, which makes them actually the easiest products to predict. In a combustion reaction, a substance, that substance, normally a hydrocarbon or an alcohol, reacts with oxygen and produces huge amounts of energy. We like to see explosions in combustion reactions. We see fire, we see flames, we see bursting open cans. Combustion reactions are big reactions, but they always produce the same exact two products, and they might surprise you. Combustion reactions always produce carbon dioxide and water. So every combustion reaction only produces carbon dioxide and water. So here are two examples of combustion reactions. The first one is ethane C2H6. This is a hydrocarbon. Hydrocarbons are carbons that have just hydrogen and carbon. That's why they're called hydrocarbons. And oxygen. Hydrocarbon plus oxygen always produces the same two products. Do you remember what they are? Carbon dioxide and water. Ethanol, which is like ethane, but it has an alcohol OH group on it. Ethanol reacts with oxygen, and guess what it produces? Carbon dioxide and water. Every combustion reaction. Last two questions on your test will be predicting the products of a combustion reaction. It doesn't matter what hydrocarbon or alcohol we put in the problem. The answer, the products of a combustion reaction are always carbon dioxide and water. Always, every time. Combustion reactions are the easiest to predict, but they can be hard to balance. But we'll talk more about that problem on a later date. This has been a beast of a lesson. You guys have done a great job sticking with it. Thank you for still being here. Thank you for continuing to watch. And when we come into class, we're going to spend some time practicing these kind of giant problems of predicting the products, determining what kind of reaction it is, and all of those goodies. We're going to really work on that together to make sure that you feel comfortable doing that, which is what you're going to be asked as a performance evaluation on the test. Are you able to predict the products? Are you able to recognize the reaction? Can you balance it? Those are the big three questions for this chapter. And hopefully by the next time we meet, you'll be able to do 2 out of 3.